Oh, it's so lovely. Greetings all. It's that time again. Magic Conundrum solved. That's right, folks. Magic Conundrum solved. Oh, there I am. No, okay. I'm going to show a series of videos. I think you will enjoy this especially. If you're new to this channel and you have not already subscribed, well, first, how the hell did you get here? Second, subscribe, hit the notification, and then after the video, put a comment about how you got here, because it's a mystery to me. Right, I can close this. I'm going to show a series of videos. First, I'm going to show a very brief video. It's very good, very nicely rendered video of the solar system traveling through space by DJ Sadu. I'm not going to play the music because it's copyrighted, but it is a really pretty cool tune. Like, totally. So, let me share. And then we're going to show some other things. That's right. Then we're going to show the reality versus the images that you just saw. So first I'm going to show some images, and there you go, good. First I'm going to show some images. This is what your imagination does with the solar system. Somebody phoning. I can't talk right now, I'm on the streaming.
Hello.
I can't talk right now.
I'm on my way down.
Oh, okay.
With the Madalena.
Okay.
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 I'll just come straight off.
Okay.
Okay.
Okay, bye. Now, obviously, there's somebody coming to the studio to drop off some Madalenas, so I will be back shortly. And I'm back. So where was I? Yes, okay. So there's this idea that we live on a globe, and this globe is traveling through space around a sun, but the whole sun and Earth and other planets in the solar system are also traveling through space within a galaxy called the Milky Way. That galaxy itself is also traveling through space, and it's all very pretty to imagine, especially when you have, you know, images like the ones I'm going to show. So let's see. Oh, solar system. Where's the solar system? Must be one of those somewhere there. So, wait. Do you see it there? That's right. Let's go back a little bit. There's the solar system. That's right. This one, the kind of turquoisey one. That's the Earth. That's the sun with a trail, because that's what it would have, wouldn't it, if it was travelling through space rather fast. But the sun doesn't have a trail. Okay, but never mind that. So this is just for ease of interpretation. The sun going around the solar system, let me play some more, with the planets, okay, very good, and this dust cloud, okay, very good, travelling around the Milky Way, doing, all the planets are doing a corkscrew, and the solar system itself is going up and down and up and down relative to that disk in the background. See that Milky Way in the background? The solar system is above it for a period of 26,000 years, and then below it for a period of 26,000 years. Yeah, that's right. That's the story. And these aren't actually at right angles to the direction of the solar system. They're at a general 66-degree ecliptic orbit. Okay? This 66 degree leaves, well, 24 degrees-ish. The difference being, well, the Earth's axial tilt. That's right, and we're travelling up, well, we're travelling in that direction towards Polaris. Okay, very good. So just 1 second, let me go straight back. Hello? So, sorry about that. That's the solar system travelling through space. Jolly good. Actually, let's play some more. It's very pretty. Wow. It's just so pretty. And what I just said about the 66 equaling 24, that's the story of the solar system. See, so here is Earth. You see, it's orbiting around the sun, but the whole thing is moving through space. Some silly dim-dims think that the only motion that the Earth has anything to do with is only its orbit around the sun. Like the other motions don't really exist. That's equivalent to you saying that when you're sitting on a train and you're putting your hand up and down and up and down on the train, that's all that matters. That when you get off the train, you're in an entirely different town. Well, that's only a circumstance of you having put your hand up and down inside the train. in the real world, it's not really got anything to do with you having put your hand up and down in the train. It's to do with where the train has been moving. That you've been moving your hand up and down, no bearing whatsoever. Why am I saying this? Because if the Earth was not orbiting the Sun whatsoever, but had a static relationship to it continuously, then, well, the Sun, aka train, would still be going where it's going, right? According to the cosmology of the globe. I will explain this clearer with a whiteboard. That's right, we're going to solve this magic conundrum. So here you've had a little visual representation of the solar system through space. Not to scale, obviously. Duh. Now, what's this? What am I going to play next? This is the physics girl. We're going to play this all the way. And I'm going to refer to her as the stoner chick. Stoner chick. Just stoner chick. Okay? Turn the volume up. Make sure everything's good. Here we go.
Our universe has some peculiar properties. Properties that couldn't be explained by conventional Big Bang theory.
Our universe has some peculiar properties that couldn't be explained by their theory of the cosmos. It couldn't be explained. The real evidence of the universe could not be explained by the theory. You see, theory is supposed to make predictions, and if those predictions fail, or if observation arises, whether or not it's been predicted, that undoes the theory, you're supposed to scrap the theory. You're not supposed to just write a patch for it. Well, we're going to see that that's exactly what they did. When they got the evidence, the proof, the observational data, it did not correspond with their theory. They did not scrap their theory. No, they just made a little patch for it. A ridiculous patch. You're going to see. Just for you who like numbers, write 10 to the minus 38. Just make a note of that. 10 to minus 38. That means 38 zeros.
For example, it's flat, meaning it's at just the right mass density that
Wait, whoa. Did she just say what I think she just said? Let's play it again.
The universe has some peculiar properties. Properties that couldn't be explained by conventional Big Bang theory. For example, it's flat, meaning it's at just the right mass density that it'll neither...
It's flat. She then says, meaning that it has a mass density that... Whoa. Flat. Let's discuss flat first. Good idea would be to not put a depiction of a cube. So instead, I'm going to, well, do this. Just a second. Whiteboard. Marker. A black one today. Let's see how well this works. Turns out the universe is flat. Oh, let's put a grid. Like so. Let's just do a grid like that and say flat. Flat. See? Flat. Just flat. This just represents flat. No end to it, just flat. Not a cube like they just showed, which is not flat. Do you see the little trickery that she just did, the stoner chick? She can't understand flat versus not a cube. Oh, silly stoner chick. Let's continue.
Expand forever nor collapse back on itself.
Oh, wait. Don't want to confuse things for the globelings.
It couldn't be explained by conventional Big Bang theory. For example, it's flat, meaning it's at just the right mass density that it'll neither expand forever...
That's not what flat means. But now she's saying also has these qualities. Has a uniform density that is uniform regardless of the amount of expansion. So the more space, the more, well, matter inside that space. You know, if you had 3 rolled up bunches of socks in a small box, and, well, there's a ratio of sock to space inside box or volume. If you now take that box, make it a lot bigger, Well, either you make those socks a lot bigger too, so they take the equivalent amount of volume, or you increase the amount of socks. Well, that seems to be what's happening in the universe according to their theory.
Or collapse back on itself. Why should it be flat? And completely opposite sides of the universe that haven't had time to interact are
completely different sides of the universe that have not had time to interact.
Same temperature. How can
At the same temperature.
possibly be?
How can that possibly be?
Were two of the biggest questions in cosmology.
So, they had a theory, and this is fact. The theory says somewhere in space there's the origin of the Big Bang. That should be detectable. Let's set up a race to detect which direction that is. They set up the arrays and went, good Lord, it's not there. Everywhere is just as old as everywhere else. There's no place that's older and younger than any other place.
It wasn't until the 1980s, with the theory of cosmic inflation proposed by Alan Guth, that we found some answers.
Now, she just said Alan Guth proposed a theory, gave them answers, but didn't say that. She said it wasn't until the 1980s that Alan Guth's theory showed us some answers. Wait.
These were two of the biggest questions in cosmology. It wasn't until the 1980s, with the theory of cosmic inflation proposed by Alan Guth, that we found some answers.
That we found some answers? You don't have any answers, Dim Dim, and I'm going to show it in this very video.
Inflation took us back to the beginning of the universe.
Okay, inflation took us back to the Big Bang. Great.
Exotic physics like repulsive gravity and false vacuums answered the why and what of
Let's go back.
that we found some answers. Inflation took us back to the beginning of the universe. And with exotic physics like repulsive gravity and false vacuums.
So, because we had a problem that the evidence seemed to contradict our theory, somebody came along and said, wait a minute, what if we say this, right? Before our theory, there was this condition, utterly extraordinary, we'll call it exotic, where oppositeness to things was happening. That's right, like repulsive gravity. That's right.
The why and what of the Big Bang. The first problem introduced by the old Big Bang theory was called the horizon problem.
Which is basically the problem of trying to understand how the universe got to be so uniform.
Now, I want you to note this man's name.
The first problem introduced by the old Big Bang theory was called the horizon problem.
Which is basically the problem of trying to understand.
Alan Guth. Nothing wrong with that. Nothing wrong with it. Cosmologist. Cosmofantasist, more like, or pataphysicist. Cosmologist. Now he's describing this problem brought about by their theory, by the way, not by the real world. Their theory brought about this problem. Say, well, that's... isn't that troublesome to you? If you develop a theory that immediately has a problem, you might take that as an indices of there being, well, a problem with the theory. Really? Did you see what I just did? I just said the words.
The why and what of the Big Bang. The first problem introduced by the old Big Bang theory was called the horizon problem.
Which is basically the problem of trying to understand how the universe got to be so uniform. Why does the universe look the same over there as it does if you look that way?
Oh, this ovoid is supposed to be the entirety of the Earth's sky. That's right. You might say, hey, this ovoid would fit perfectly well over, well, a kind of ovoid map of the Earth. That's right, a bit like yours truly's. But, no, this is supposed to be representing two hemispheres. That's right. You might say to yourself, hey, how can you represent two hemispheres with an ovoid? The answer is, you can't. Don't be stupid. Of course you can't. But let's pretend that you could, and this ovoid was the entirety of the sky, aka the observable universe, And from Earth, looking at the night sky, aka the observable universe, I don't have it. Wait, Mum, wait.
I'll go down.
Black coffee, please.
Black coffee.
One honey.
One honey.
Yes.
When I come up with the milk.
Yeah, so that's the situation. Entirety of the observable universe, right there in that ovoid. The theory predicted somewhere there would be a place of either higher density energy or least energy. There was a bit of a, two different camps. There would be the highest amount of energy at the region of the Big Bang versus, no, that would be the region with the least, like the center of the pond where you've dropped the pebble. That's the area that's going to become flat and still first, whilst the rest of the area still has ripples or consequence from the ripples. See? Right. Now, but they looked and they went, good Lord, it's all just as old as everywhere else. That's the horizon problem.
Why was this a problem? Well, think of a cup of tea. If you pour milk into your tea, it'll take some time for...
Wait a second, that's not flat. That cup of tea is not flat. Why would you show a problem that's a consequence of flatness with a non-flatness scenario? But let's continue. Let's let her. She's a stoner chick, remember.
Molecules to interact and eventually come to about the same temperature. But it won't happen instantly. The same is true on a larger scale. The fastest any two objects can interact is as soon as light has had time to travel between them.
No, as soon as radiation, light is a form of radiation, yes, but look, the majority of the forms of radiation are not light. So, as soon as, there can be interaction. That's the soonest, not before then.
According to conventional Big Bang theory, light hasn't had time to travel from one side of the observable universe to the other. So, why...
Okay, now, just to explain for some of the globe dim-dims, it doesn't need to have travelled from one side to the other. All it needs to have travelled is from the centre, where the Big Bang happened, to the outermost extremities. But of course you don't know where that centre is, because it's not actually there. It's a Santa Claus fantasy. It's wrong, and the evidence is saying to you, look, retardo McFardos, it's wrong. Your theory's wrong. Look.
They'd be at the same temperature.
So inflation gets around that, and...
So, inflation gets around that. Not inflation answers that. No. Inflation gets around that. You have to understand, the man you're looking at now has been paying his mortgage and his children's education and his extracurricular activities with boys or girls, who knows, from being a charlatan. That's right, from being a charlatan. That's right, this man has been being paid to continue to be a charlatan. To continue to say, yeah, but you see, if you say this, then you can just sidestep that other thing over there.
Really very simple.
There you go. And listen to his explanation. Just a little bit of NLP. Okay? Now, if he says it's really quite a simple explanation, then gives you an explanation. If you go, I don't get that, your brain automatically says, you better not acknowledge that thought, otherwise you'll have to acknowledge that you're retarded. Because he said it's quite simple. If you don't get it, and he said it's quite simple, means you're stupid.
Had time to travel from one side of the observable universe to the other. So why should they be at the same temperature?
So inflation gets around that in really a very simple way.
See? In really a very simple way. Now let's see what this very simple way is.
Trace back the universe that we're looking at now to what it looked like before inflation. It was vastly smaller than anybody would have thought without the inflationary theory.
Vastly smaller is not an exaggeration. Before inflation, everything in our observable universe fit in a volume a billionth the size of a proton.
How do you know? We don't. We just think it. Okay.
The universe went through two expansions, inflation and after. Both expanded space by a factor of 10 to the 28, but the second expansion took 13.8 billion years. That first expansion, inflation, took 10 to the minus 38 seconds.
Wait, what? 10 to the minus 38 seconds? What does minus 38 seconds mean? Right, if you take a second and you want to see what 100th of a second is, well then you can go, okay, so you take a second, a period of time, You can half that, that would be 50, and then you can half that, that would be 1/25th, and then you can, okay, and you can kind of, you know, idealize an answer. Okay, 1/100th of a second, that's okay, got it. What if it's 1,000? Okay, well, 1/100th of a second times 10, whoa, a lot narrower sliver of time. That's 1,000th of a second. What about a 100,000th of a second? What about a 1,000,000th of a second? What about a 100 million millionth of a second? And that's not even the whole number of zeros. That's to say, in a ridiculously brief period of time, this expansion thing happened. I say this, ridiculously brief period of time, much faster than the glint in someone's eye, or the sneeze, or the just so much briefer than that. I mean, if you were to compare, say something was travelling at a light year, the speed of a light year, and it was to cross a hair, okay, the width of a hair, okay. Well, if it was, we were to make that hair ratio, oh, well, it would be very big. It's absurd, completely absurd to make these comparisons, but that's what they do. Never mind that. Ridiculously brief period of time. I'm going to say it one more time. In a ridiculously brief period of time, this expansion thing happened. During this expansion thing, with this in that ridiculously brief period of time, the conditions were exotic physics. How long for, sir? A brief period of time. How brief? Very brief. How brief? Even briefer. Okay.
Just an unfathomable rate.
An unfathomable rate. Yes. In an unfathomably brief period of time. Yes.
You goose.
And it was during the time before inflation, when the universe was incredibly tiny, that there was plenty of time for every piece of the universe to communicate with every other piece.
Now, what period is he referring to that gave plenty of time? This 10 to the minus 38 second period, that ridiculously brief period of time, that's the period. He's not referring to the other one. No, he's referring to this ridiculously brief one, the 10 to the minus 38. That's what not this 10 to the 28. No, the 10 to the minus 38 is what he's referring to.
But the second expansion took 13.8 billion years. That first expansion, inflation, took 10 to the minus 38 seconds.
This is the period he's discussing. In this period, exotic physics. In this ridiculously brief period, ridiculously brief, plenty of time. That's how he describes it. Plenty of time. You know, if you pour milk into a cup of tea and you look and you see how it resolves and it takes a while before it's all ubiquitously spread out, dissolved amongst the volume of tea. Well, that's a period of time between when you pour it and when it becomes a homogeneous substance. Well, the universe seems to be homogeneous. But it can't be homogeneous because of the different periods of times involved with different things at different distances. But never mind that, you see. At the ridiculously brief period of time way back when, at that point, that ridiculous 10 to the minus 38 second, plenty of time for things to associate with each other and say, hey, remember your temperature, dude. Remember your temperature.
Just an unfathomable rate. Back to you, Goose.
And it was during the time before inflation when the...
See, this is what he's talking, the time before inflation. That was that 10 to the minus 38.
This was incredibly tiny, that there was plenty of time for...
That's when there was plenty of time. That's right.
piece of the universe to communicate with every other piece. And
You see, what he's saying is, look, at that point, everything was just as hot as everything else, right? Yes, right. Well, there you go. That's the answer. Whoa, whoa, whoa. We're not talking about then. We're talking about how it is that things are like that now. The equivalent would be this. There's a great big cauldron of soup in the center of a circular Basque country gathering, and they're all going to have some of this delicious fish soup. There's a great big cauldron. There are tables that are more far away and tables that are closer. And all of the tables are going to have bowls of soup on them. The soup in the cauldron is all the same temperature, but the soup at the farthest tables is going to be of a different temperature than the soups nearest to the cauldron once it's all been ladled out. Do you see? They can't all have the same temperature regardless of the fact that at a point in time they all shared the same temperature. You understand? It's just not possible. It doesn't happen. It's like grandparents being as old as their grandchildren. It doesn't happen. It's a silliness. That's why I say that man gets paid to be a charlatan.
plenty of time for it to come to essentially a uniform density of energy. And
At that 10 minutes 38, that was plenty of time for everything to have the same state. Great. We're talking about way after that, dude. After the soup was ladled out. After it was ladled out, how come it's all the same temperature?
temperature.
So now we know the universe was super tiny.
Now we know the universe is super... No. Now you've heard a charlatan explaining a different way of considering the conditions of the Big Bang. That's all. It's just a different charlatan. You don't know anything. Now the most you know is that that's what that charlatan says. Doesn't mean that what he's saying has anything to do with knowledge.
The true genius of Guth's theory was not the incredibly tiny universe.
The true genius was not describing the conditions of the incredibly tiny universe. That's not his true genius.
How it could have expanded so fast.
Oh, it was how it could have expanded so fast. Very good. Let's see.
Inflation provided the mechanism for expansion. Repulsive gravity.
See, inflation, which, by the way, is implied in the original seed of the idea of the Big Bang. Inflation, that things move away from each other. His genius was saying, what made it inflate so fast? Well, you might think it would inflate at the speed of light, but nope. It inflated faster than that. Oh, I thought you couldn't have faster than... Well, never mind that. We're talking about a state of the universe when it was exotic. It was exotic physics. Not the physics we have now. No, the physics of holidays in Brazil or Hawaii or Israel or exotic places. That was the physics.
His theory of gravity was always attractive. There just was no other option. But it turned out that this more complicated theory of general relativity actually allows for the possibility of a repulsive form of gravity.
How can it allow for it? Well, it's like this. It's a theory, it's written in paper, right? Yep. And paper still exists, right? Yes. And ink with which to write still exists, right? Yes. So how can the theory of relativity explain this? Well, we just said that it does. We wrote some more, and we said, oh, and also gravity can repel. Okay. Well, it turns out that the special theory of relativity also says, and by the way, if you need to make extra stuff up, just make it up. And make it up from any point after this one.
In very specific circumstances, gravity can provide a push, not...
Going back.
General relativity actually allows for the possibility...
Oh, sorry. Was it general relativity?
Gravity was always attractive. There just was no other option. But it turned out that this more complicated theory of general relativity...
Oh, sorry. Apologies, physicists. I said special theory. No, it was the general theory.
actually allows for the possibility of a repulsive form of gravity.
Yes,
Now, this stoner chick, by the way, I love stoner chicks, I have to say, okay? And I like this girl, she's very attractive and very charismatic and nice. But that's not the point. I'm saying stoner chick, so you can say like, yo man, you're blowing my mind. So, when he explains what he's just explained and they cut to her, what does she say? She says, yes! Like, we have the answer. Phew! Good thing we have the answer. Watch.
yes, in very specific circumstances,
Oh, very, very certain affirmative. Yes, in very special circumstances. Gonna go back. Yes. Better not doubt that, or you'll be a moron if you doubt that, because she just said it emphatically.
circumstances, gravity can provide a push, not a pull.
Go back.
Actually allows for the possibility of a repulsive form of gravity.
Yes,
Is there any evidence of that? Nope. Well, why do you think that? Because if we don't think that, then the Earth is flat and we're just charlatans. They can't own up to being charlatans, so they're not going to. Yes, under special circumstances, gravity can repel. Oh, and time can happen before itself. Oh, and so can light. Oh.
In specific circumstances, gravity can provide a push, not a pull. It comes from something called the false vacuum, a state of matter in the early universe that allows expansion of space while the mass density stays constant.
See, that's my example with the socks in the box.
That understanding for the mechanism of inflation brought a solution.
Okay. She just said that understanding of... No. That invention, that concoction, that word salad. That's right. It's not an understanding. It's a made-up set of terms.
False vacuum, a state of
False vacuum. What does that mean? Well, not vacuum. Oh, okay. The end. No. Wait. Let me tell you some more. Well, what are you going to tell me? Well, right. Well, this false vacuum, it actually pushes things away from each other. Why? Well, because, dude, look, we got the readings. It says all of the night sky is just as old as all the other parts of the night sky. That's not supposed to be the case. We've got to concoct a way of explaining why it is that way. Otherwise, we're all fired and everyone will know we were just talking shit all the time, dude. So play along.
in the early universe that allows expansion of space while the mass density stays constant. And that understanding for the mechanism of inflation.
That understanding? Like, that made-up story about... Okay, that made-up story about...
A solution to the horizon problem.
Oh, give us a solution to the fact that everything's just as old as everything else in the sky when it's not supposed to be according to your theory. Yeah. Oh, I see.
Second problem was called the flatness problem. Why is the universe so flat? And what...
Why is the universe so flat? We have millions now of flat earthers going, it's all flat. I mean, apart from mountains and whatnot, buildings and... It's flat. Why? It's all flat. Then you have physicists going, it's flat. Why? It's all flat. And they're all confused. How can it be flat if it's spherical? Like, because it's not spherical, dim. But all the ways our teachers told us about the flatness were showing spherical objects. Yes, so it's flat and spherical. Like, no, they just showed you using spherical objects. They couldn't show you with just flat objects, because, well, then you'd see that they were just full of shit and charlatans.
What do you mean by flat? Well, the curvature
What do you mean by flat? Well...
of the universe is defined...
What do you mean by flat? The curvature of the universe is defined by...
Second problem was called the flatness problem. Why is the universe so flat? And what do I mean by flat? Well, the curvature of the universe is defined by the mass density of space, or the amount of energy and mass per volume.
No. This curvature is or sphericity. So a sphere necessitates curvature all kinds of ways. Okay. Now, this mass density and equilibrium doesn't work like that. No. It works more like, well, a layer of paper. Just a layer. A layer has a certain amount of thickness. There's your y-axis, if you want to consider, z-axis. Okay? A certain level of depth. That's your up and down. And then you've got the other two axes, see? But no, let's show it with a cube. You shouldn't do that. You should maybe zoom in on a layer of paper. Say, see this paper? That's flat. It has a thickness, right? Yes. What is that thickness? We don't know. All we know is that it's all the same consistency.
There's a lot of matter. The universe is closed and collapses back in on itself. If there's not much matter, the universe is open and it will expand forever.
Okay, let me just go back.
Energy and mass per volume. If there is a lot of matter, the universe is closed and...
Right. If Santa Claus is evil, he steals all your gifts.
Collapses back in on itself. If there's not much matter, the universe is open and it will expand forever.
If Santa Claus is tricksy, he gives you gifts, but then he takes them away.
If, however, the universe is in perfect balance and the density is exactly critical density, the universe will be flat and it will continue.
The universe will be flat. Is it flat and spherical? Yes. No, it's not. It's only flat. Is Santa real? No, silly. The gifts are real. The love from the people who buy the gifts is real. That's the real part. The gifts are real. The happiness is real. The cold or the heat, it's all real. The Santa Claus is the illusion bit. It's the curvature that's the illusion bit. The universe is flat. And I'm going to show the answer to the conundrum with the magic whiteboard.
To expand forever, but at an increasingly slower rate.
Now here comes a, whoa, you're blowing my mind, dude.
So it will eventually stop, but when time reaches infinity.
The universe is going to continue to expand in a nice stable state or rate until it reaches infinity. Whoa, dude, you're blowing my mind. Until it reaches infinity. What infinity? Infinity of space, or infinity of time, or infinity of both? In which case, it can't be reached. If it could be reached, it would be finite and not infinite. Listen.
Exactly critical density, the universe will be flat and it will continue to expand forever, but at an increasingly slow
forever. Until
rate. So it will eventually stop, but when time reaches infinity.
It will continue to expand forever, but it will stop. Well, then it wasn't forever. That's okay, because I'm going to say at the point of infinity. Whoa, man, you just totally shifted dimensions. Whoa. Yeah.
The mass density we've measured so far appears to be exactly critical. Why it?
What does this mean, exactly critical, the mass density? It means homogeneous, the same everywhere in space. And when they're talking about space, they're not talking about, well, the space between, your kitchen and your bathroom. They're talking about the out there, the blackness of the night sky. That up there. That's what they're referring to. That's what they're studying. The evidence is saying, hey, homogeneous, same, and just as old. Everywhere you look, just as old. Everywhere. There's no place older or younger. And because they concocted this theory of a beginning to it, they have to now do this, well, mental gymnastics to explain how it is that the evidence is saying just as sold everywhere as everywhere else, when their theory says should show a discrepancy between one region and another. We don't know in which direction these regions would be, but we know that there should be there because that's how logic works, and that's how the real world works, and that's how physics itself work. So, because it's not saying this, they're saying, well, what must be the case is forget the laws of physics that are reasonable and rational, that the actual, real, testable laws of physics, forget those. There must have been a different set of laws of physics that were exotic, that did not have the same elements as standard physics. No, we just said that we were putting that physics to the side. No, it was a different physics, dude. Yeah, it was that other physics that set up the sky.
That. In fact, if it had started even slightly open or closed, it would have been pushed even further away from critical density over time by the expansion of the universe. Just like the longer an arrow has to travel toward a target.
This is brilliant. The longer an arrow has to travel towards a target, listen,
the straighter you had to have initially shot the arrow. But
that's just wrong. Just wrong entirely. I'm going to go back. I shoot. I enjoy archery. There are other people who enjoy archery. We know about shooting targets with arrows. First, it's a very poor analogy. You don't shoot targets with arrows by pointing exactly at the blank. You have to point higher up so that the arrow will reach the blank. Okay? So you're wrong. But listen.
Even further away from critical density over time by the expansion of the universe. Just like the longer an arrow has to travel toward a target, the straighter you had to have initially shot the arrow. But
no. If you're going to use this analogy, you would say, just like the longer the arrow has to reach the target, the more momentum it must have had. Not the straighter it has to be. That's retarded. The more velocity, the more momentum, the more speed, the more power, the more intention to go ahead in a straight line. Not the more in a straight line you have to have. This is how these guys convince themselves that they might not be charlatans. And this is how they convince their friends around them that they're very bright. Because their friends are too stupid to go, I think you're full of shit, you. Come to the archery range with me. Let me explain something to you.
And pushed even further away from critical density over time by the expansion of the universe. Just like the longer an arrow has to travel toward a target, the straighter you had to have initially shot the arrow.
The longer the arrow has to travel to reach a target, the straighter. No, that's literally the opposite. The longer it has to travel to reach the target, the more of a parabolic arc it would have to do.
We're so close to hitting a bullseye. We're so close to critical density. Why? Inflation forces the universe toward critical density. How?
Well, in the conventional Big Bang theory, the universe gets larger, but as it gets larger, it gets much, much less dense.
So, as it gets larger, the space, the emptiness between the objects in that space, it grows, like the box with the socks. You make the box bigger, but you don't increase the size or the quantity of bundles of socks. Well, there's more space per sock.
Inflation, the universe is getting larger and larger, and hence flatter and flatter at a fixed mass density.
And flatter and flatter. But you see, because they've done this mental gymnastics where flat means spherical, or flat means this other thing. We just use the word flat to mean critical density. That's what we mean. We don't mean flat. And I know we've got the term critical density to refer to, critical density. And we know that critical density could be explained with, say, yeast and bread. You know, you roll out some dough, and it has yeast, and you've put some kind of restriction on it so that it won't grow up as much as it grows sideways, right? And it will grow up a little bit because it will push against that restriction, but it will also grow sideways and remain, you know, maybe a centimetre thick, and maybe grow a tiny bit up once it grows very much sideways. And yeah, no, we're going to say that we're using the word flat to refer to critical density.
General relativity implies a direct relationship between the mass density and the
There's a cube.
geometry of space, or the flatness. So, as
Or the flatness. Now, we're talking about the geometry of space, specifically its flatness. But here we have a sphere, a saddle, and a flat grid. Now, if they showed mass density, they don't have to show a picture, okay? And geometry, and they only had the flat grid, it might be a bit easy for people to see. But instead, some people can go, that's interesting, because you see the flat grid, that's really just a segment of the sphere. That's right, yeah. But not really, because they explain that it's not a sphere. Okay, so
expands, the geometry gets flatter.
oh, and now let's discuss the saddle.
Imagine space like the surface of a balloon.
Imagine a sphere. How about we imagine space as the surface of a pond in which water is being poured, and it's growing because, well, water's being poured. But no, let's not do that. Let's do a balloon.
You blow the balloon up, the surface gets flatter and flatter. Space does this in 3 dimensions.
Space does this in 3 dimensions. Like, you know how your theory predicted a point of beginning and it was wrong? Yeah, well, this part is also wrong.
And as space gets flatter, we go back to our relationship between geometry.
See, things can't get flatter and flatter infinitely, because once it's flat, it's not going to get flatter. It's going to continue to be flat. See the meaning of words?
And mass density, and we find that the density is pushed toward critical density.
Oh, now they show the flatness. Good.
In fact, it's pushed very quickly toward critical density since the expansion of space during inflation is exponential, which
Right, that's silly, but remember that expansion of space in 10 minus 38 seconds? That mega brief period. Listen.
find that the density is pushed toward critical density. In fact, it's pushed very quickly toward critical density since...
You don't say! 10 to the minus 38 seconds, I'd say that's very quick.
Expansion of space during inflation is exponential, which explains why we're so close to critical mass density.
And wait, it's exponential, so at the end of this, so picture, okay, tick, tock, okay, this break between the tick and the tock, okay. Let's imagine brightness as a way of visualizing, okay. So the tick, pretty dim, the tock, bright, okay. It's exponential, okay. So in this 10 to the minus 38, that's how quickly it became bright. It's just like very quickly, in a very brief period, boom, exponential, okay. Not you understand exponential? Yeah, you okay.
Boom! Flatness problem solved.
No, flatness problem confirmed, not solved. And that's what they do, these dim-dims. They say, boom, flatness problem solved, yo. It's like, no. Flatness problem confirmed. Is going to be solved today by yours truly on this very hangout with a whiteboard.
So you may be wondering, if inflation theory was so revolutionary and imaginative, why haven't we heard more about it? Well,
because people can see bullshit in it. That's right.
inflation is still a hot topic of debate.
In other words, there are some people saying, not true, don't believe it, show me. I don't believe it. You're asking for special circumstances. That's special pleading. Nope, you're not allowed to do that. Not only is it unfalsifiable, it sounds like a crock of shit. It sounds made up, and Even within the theory, there are huge problems, including this. Well, that region farthest away, just as hot as that region. No, different period of cooling between the two regions. See, closest to, less time for cooling. Farthest away, more time for cooling. So no, not buying it.
First, it solves many of the problems of conventional Big Bang theory.
It doesn't. It doesn't. Only to dim-dims. Only to people who are stupid, like the majority of the globe cosmologists.
And is widely accepted throughout the scientific community, but like all good...
No. She just started off saying there is still a point of contention.
Toward critical density. In fact, it's pushed very quickly toward critical density since the expansion of space during inflation is exponential, which explains why we're so close to critical mass density. And boom! Flatness problem solved.
Confirmed. Flatness problem confirmed. Okay.
So you may be wondering, if inflation theory was so revolutionary and imaginative, why haven't we heard more about it? Well, inflation is still a hot topic of debate.
A hot topic of debate means some people are saying, I think you're interpreting it wrong, it's really this way. And other people saying, I think you're full of shit.
Discussed, it solves many of the problems of conventional Big Bang theory. And
it doesn't. It doesn't solve anything. But never mind.
Widely accepted throughout the scientific community, but like all good theories, it has to make more predictions which we then observe.
And it can't, and it doesn't, and it hasn't made any. It has made not a single prediction that has been observed. Not one.
Hoping for more observations that support inflationary theory, or whatever theory that might improve upon it.
Or whatever theory that might improve upon it? Improve upon what? Upon inflationary theory? Or upon the theory of the Big Bang? That's a bit word salady. Be clearer.
What we're working toward. Thanks for watching.
You're welcome, Stoner Chick. Now, let me go and look in the chat for a second. By the way, 12,000 views on yesterday's Hangout. Gosh, shocking, look at that hair. 12,000 views on yesterday's Hangout, folks. No idea what's happening. Well, maybe there's a flat earther in YouTube. Now, come on, guys, okay? Be real, be sensible. What are the chances that in the framework, the thousands of employees who work for YouTube, that there's at least one flat earther? What are the chances of that? Is it impossible for there to be a flat earther who works for YouTube? No, it's not impossible at all, is it? No. Okay, so it's possible. Okay. How probable is it? Oh, that's a good question. So, just saying. Right, now, Roy Christopher, everybody in the chat, greetings. I'm not going to go through everybody's name. I'm going to instead go on. This is just a rehash, really, of the silliness that we showed earlier in this week or last week. Yeah, just recent Hangouts, okay? Now we're going to go, and this is just, well, for the... Because it's fun for us flat earthers to see the silliness of the globe. It's just fun. I mean, it's fun to me at least to go, my gosh, if I thought back when I was a globeling, if I'd come across this back then, I would have doubted the globe. I'd say there's something very wrong with this. I really would. Now, there are people out there whose thought process led them to the conclusion that there's something very wrong with what's being presented before Marv Powerland and before Eric Dubay. There's one called Adam Dwyer who came to the conclusion just from looking at the evidence. So, that was Stoner Chick. Now we're going to go through this again. This is just so good. I mean, there's just so much meat on them bones. So, if the universe is only 14 billion years old, how can it be 92 billion light years wide? Given that for 92 billion light years, there must be 92 billion years. But there's only 14 billion. Not really. It's 13.7, but never mind. It's not really 13.7. That's stupid. It's an infinite. Infinite. The universe is infinite in age. That's right, it's eternal. They can't put that into their equations because then they all get fired. So let's go. Well, guys, just enjoy. You know, I'm chilling, you chilling. Let's enjoy.
When we look out into space, we are not only looking at things that are far away, we're looking at things that existed in the past. For instance, the sun is about 9.
Bearing in mind what I showed yesterday about the path of the light, this now has a different level of absurdity to it, does it not? I think so. And I will show it with the whiteboard.
3 million miles away, and it takes light about 8 minutes to get here. Thus, when we sit down in the morning with some toast and our first cup of coffee for the day and look at the sun, we're seeing it not as it is now, but as it was when we put the bread in the toaster. Time and space are inextricably intertwined when we talk about how far away things are.
This time and space are inextricably intertwined. It's like, they're two distinct concepts. You have to discuss or have both of them in mind when discussing things travelling and distance. True. The inextricably intertwined doesn't mean, therefore, you can just lump them up and say it's just one figure, one thing to consider, and then we can move on to something else. Like, no. You must bear that in mind. The space through which is being travelled and the time over which that travelling is taking place. You can't ignore that.
Especially true when we talk about large-scale structures of the universe. We even have a distance scale called a light year, which is the distance that light travels in a year. In more familiar terms...
Now imagine, just for the sake of argument, imagine that light didn't travel. That's right. Just imagine that. Imagine that what happens is you energize a filament 50 miles away. That filament is going to radiate. I mean, you call it a filament. It isn't. It's a whole bundle of filaments that radiates out. If it's a bulb that has no cowl, it spreads out in all directions. Okay. So you have a bulb. It spreads out in all directions. This bulb is energizing filaments. You're 50 miles away. Oops. You're 50 miles away. And the filament is energized from 50 miles away. Great. And it's energized now. But it doesn't arrive at your eye for a millisecond, apparently. It's like, okay. And now it's arriving at your eye. It's not arriving continuously a microsecond behind itself. It's now arriving instantaneously. But these silly boobs, they think that no, what happens is it's always arriving behind itself. Or you're always seeing the bit that was before. It's like you don't understand phenomenology very well. They don't. So let's continue.
A light year is 9.5 trillion kilometers, or just shy of 6 trillion miles. We use the unit light year because nothing travels faster than light.
Apart from when we need it to, then we say it does.
It's very convenient. But it is most convenient when we talk about the size of the universe. Astronomers have determined the age of the universe very precisely. It is 13.7 billion years old.
How did they establish that? Trade secret is a trade secret. Well, it can't be a trade secret if it's being taught at university, so come on, cough up. How did they establish this? Well, they just said so. Oh, okay.
Exactly how we know this is perhaps the subject of another video, but...
Exactly how we know this? They don't know this. This is just an imagination game.
Moment, let's take that number as a given.
Okay.
If we do, we can ask a very simple question. How big is the visible universe?
How big is the visible universe? Oh, 4.6 billion years old.
There are lots of tricky ways to think about that, but let's start with...
Wait a second, because I just said 4.6 billion years old. Where's that? That's how old the Earth is. Well, what's that? What bearing does that have on anything? Well, light. Light, 4.6 billion years worth of light. Is light arriving here that hadn't actually been transmitted yet, or was it transmitted already? It's just a guess. I mean, I can just spitball as much as you guys, right?
It's the most obvious. We can't see the universe before it began because, duh, well, that's what beginning means.
We can't see the universe before it began because there'd be nobody here to do any seeing. See? See how it breaks down the thinking? It's like, hey, if we look in that direction, we can look at where there was nothing in the universe, not even us. Like, oh, really? You can look back to when there were no humans? That's an interesting way of looking at things. That sounds a bit like you're discussing the Genesis before there were humans.
When the universe began, it was filled with light, which then traveled through the cosmos.
Now, let's first of all do a little bit of a balancing act and say, when the universe began, it was filled with light, so that all the Christian students can go, well, this doesn't challenge my religion. My religion says God said, let there be light, and there was light, so good. What else, Professor?
And if the universe...
But wait, it wasn't filled with light, it was filled with blackness. That's right, you're going to hear that later on. That's right. You know the explanation when somebody says, look, so I got in my car and I went to the shop, and then I came home. And you said, what time did you leave? Well, I left at 3:30, because that's when I got on the bus. Like, wait, what? Yes, I got on the bus and went to the cinema. Like, but you just said you got in the car. Well, yeah, but no, I'm saying I got on the bus. Like, okay. So when they say the universe was filled with light at the Big Bang, and later they say, actually, it was so hot, there wasn't even light. Like, oh, right. So you mean it wasn't even, like, light? That's literally the opposite.
began 13.7 billion years ago, and we're just now seeing it arrive, it had to...
Now, how would we be seeing something that was emitted 13.7 billion years ago arrive now if it has been travelling at the speed of light? We would have to be 13.7 years away from its point of emission for it to arrive now. We are not 13.7 billion years away, so you can't. I will show it with a whiteboard.
Traveled 13.7 billion light years before it hit Earth. And to make that point solid, astronomers can
To make that point solid, astronomers can show you this image and say, you remember when I said the universe was big, bright, black? Well, now that I said 13.7 billion light years, here's an image of eternity. That's right.
see light from shortly after the universe began.
No.
It's called the cosmic microwave background radiation.
No, it's an image of eternity. That's right. Copyright, trademark, Antonio Subirats, The Book of the Sun. Cosmic background radiation is an image of eternity.
And it is the oldest thing we've ever seen.
No
It is hitting
shit,
the Earth.
Sherlock. It's eternal. That's how old.
Every direction, and it is, to all intents and purposes, a photograph of the birth of the universe.
It's a photograph of eternity.
13.7 billion years ago.
No, eternal.
Accordingly, it would be reasonable to say that the visible universe consists of a sphere centered on the Earth with a
It's flat, remember?
radius of 13.7 billion light years. Boom. Done.
Now, let's go back.
Let's say that the visible universe consists of a sphere centered on the Earth with a radius of 13.7 billion light years.
Jolly good. Now comes the whiteboard. Whiteboard, marker, oval and oval. Okay. Look, folks, we have an oval, and here there are continents and water. Oh, okay. It's oval. And here, when they look up into the sky, no matter where they're looking from, they're looking at this oval. This oval has eternity imprinted on it because it's always been there. Okay, they're not looking at stars, they're looking at the radiation between the stars and between the galaxies. Okay, that's what they're looking at. From here, they look up, and all of this has radiation coming down towards their sensors, wherever their sensors are positioned. Their sensors are positioned to look up, because up is where there's the least amount of refraction. They don't look out horizontally, they look up. This is what's happening, folks. This is the solution. Now, all of this having the same amount of radiation coming down from all of the different points, it's a problem for the globe, not a problem for this. In fact, necessary for this. Oh, that's interesting. So, the theory of that necessitates the universe as it is, without cockamamie stories, but the theory of the globe, so here's a sphere, and I'm going to draw some segments so you can see it's not very good. Start again. A sphere, come on, a circle, and longitudes. Like so, you know what I mean. Okay. Now, this sphere, and I've just drawn these longitudes to make it easy to see. It's a sphere, it's not very good. Okay. On this, as opposed to what I showed a minute ago, all the directions looking up in the same direction, having cosmic background radiation arriving from the same direction, all of it, down. Here, cosmic radiation, this is not working so well, so I'll use the red one. Cosmic radiation, they're looking up in that direction, and cosmic radiation is coming down in this direction. But they also look up from here, and cosmic radiation is coming down from that direction. And they also look up from there, and cosmic radiation is coming down from that direction, and so on, and so forth. Because they think they're on a sphere, and they think that when they're looking up away from a central point of a globe sphere, in which case all of the direction are radiating opposite to all of the other, if you want to have a counterpoint, opposite to all of the other directions. So the radiation is coming in from all of the possible other directions. Well, that goes against the theory of the universe, and it goes against the actual observation, because radiation can't come in this direction unless it has been emitted by something over there, and come in that direction unless it's been emitted by something over there. And the way the universe works, you don't have something that emits radiation inwards ubiquitously from any chosen grid. So any chosen indexical point. Now I'm going to do this. Here is the Earth. Come on, start drawing. Okay, now I'm saying, it. Now I'm saying that that's the Earth, and this is what's emitting radiation. Good gosh, but wait. If we look at, if we say this is Mars, then we say that that's where all the radiation is going to. It's like, oh, hello. This sounds like bullshit, really, doesn't it? It does. It sounds like bullshit. Now, this is important for people to understand who believe in the globe. The globe was given to you by narcissists, by people who don't really understand reality very well. They're not capable of acknowledging mistakes, so they don't acknowledge them. They don't acknowledge them. If you catch a narcissist outright, if you have video evidence of them doing something that they have been gaslighting you with, saying that they never did, they will try to give an explanation that says that what you're seeing in the video is not what actually happened. That's what happens with narcissists. This idea of the universe that's being presented by the cosmologists of the globe is narcissistic. That's why there's so much word salad. That's why there are so many internal contradictions. So I'm going to go back, play some more. In fact, what I'm going to do is I'm going to display in a different way so that I can join you in the chat. Just give me a second. Ay, ay, ay. If the universe is only 14 billion years old, how come it's 92 billion years big? Like, no, oh, right. Here we go.
Boom. Done. Except that this is completely wrong. That's one of the sneaky things.
See that there? That's gaslighting. So here's an explanation. There you go, see? Fully explained. Except it's not really, I'm just fucking with you. Because that's what he's just done. That's what he's just done. So this is what happens, see? They explain and go, so you've got that, right? You go, yeah. Well, you're wrong. Because it's this other thing. Really? Listen.
Radius of 13.7 billion light years. Boom. Done. Except that this is completely wrong. That's one of the sneaky things about science. It can fool you if you think too fast. Sometimes you have to slow down and mull things over.
Wait a second.
If you think...
It can fool you if you think too fast. It's like, I think what he means is, it's best if you absorb it without thinking. That's the best thing to do.
About it for a moment, you'll realize that this way of thinking assumes that the universe is static, and, at least on average, distances between objects aren't changing. But we know this isn't true. To begin with, the Big Bang happened. The universe is expanding, and it used to be expanding much faster than it is now. And that means that the simple answer isn't good enough. I don't want to get too deeply into the details of the Big Bang, but it boils down to the idea that the universe was once smaller and hotter and has been expanding since the beginning. I made a video about it if you want more. And that expansion is key to understanding what is going on here. We start by imagining what the universe looked like when this microwave background radiation was emitted. It was hot everywhere. No place was special. Well, I guess one was, kind of. And that place is the current location of Earth. But at that moment, it looked like everywhere else.
Now, he just said, at the beginning, when everything was expanding, everything was the same, apart from this region that was special, which we're going to say is the region where Earth is now. Except that region didn't quite exist yet, because it hadn't been encompassed by the space-generating, expanding flashness. It didn't exist, it hadn't reached. So, this is equivalent to saying, look, here's a book. At this point, character Roger is introduced. Roger is very special. Why is he special? Because way back when, at the beginning of the book, where the pages were being written, at that point there was a special page in the future of the book where Roger would be written. Like, what the heck is wrong with your thinking?
Now, there was a sphere centered around that point and at that time, and that sphere is the origin of the cosmic microwave background arriving at the Earth now. That radiation moved toward the Earth at the speed of light, and it took 13.7 billion years to get here. If we look at a sphere smaller than that special sphere, that light has already passed the Earth, and we can't see it. Light from a bigger sphere isn't here yet, so we don't see it either. When this light...
I'm going to have to pause, get the whiteboard out. For the dames. Okay, whiteboard, marker, hopefully works. Here's a pond generated by a pebble being dropped there, and it took X amount of time for this to reach here. Okay, what's this amount of time? They say 13.7 billion years. Great. For this to reach here, how long? 13.7 billion years. Wonderful. At which point did Earth start to exist? 44.6 billion years ago. Very good here. Yes. Hey, that can't reach here. 14 billion years or 13.7 billion years, because, well, it's gone beyond. See, it's gone beyond. This idea that it's like, oh no, the Earth is here. It's like, no, the Earth is not here. The Earth is here. This is where Earth started existing, and as this that continued to move, so did this. So that this is now the 13.7. You see? The Earth is not at the edge of the supposed cosmology. It's like, how retarded are these cosmologies? Or, in fact, how retarded do they think their students are? Because you know what, folks? A bright person studying cosmology or astrophysics now either has to know that this is all bullshit, repeat it to pass the exams, get their degree, and then get their PhD, and then start writing to debunk all of that bullshit and hope that the papers they produce will be published. But if they're that intelligent, they'll know that they won't be. So they will drop out. That's right. So what I'm going to start doing, folks, in the next few months, I'm going to find where there are cosmology lectures at Manchester University. I'm going to sit in. And at the end, when there are questions, I'm going to ask questions. That's right. Now I'm going to go back to the gibberish the nincompoop is explaining.
Emitted shortly after the Big Bang, this sphere's radius was about 42 million, that's with an M, light years away. Naively, you'd expect that this light would have taken 42 million years to get here, but it took 13.7 billion, and that's with a B, years to travel to Earth. And the reason that it took so long is that space was and is expanding. Now, if you think about that, it means that space between that sphere and the location of the Earth had to be expanding pretty fast. Otherwise, the light would have passed by the Earth long ago. I mean, it was only 42 million light years, and it's been nearly 14 billion years. So that sphere from which the microwaves were originally emitted also grew in size. And, in the simplest calculation, that sphere would now be 41 billion, that's with a B, light years away. However, it turns out that the simplest calculation isn't quite right. You see, about 5 billion years ago, an energy field that we call dark energy became important. Dark energy is a repulsive form of gravity, which means that the expansion of the universe isn't slowing down, it's accelerating.
Sorry, I just read a comment from Del Beyond the Imaginary Curve. Yes, so let's see. I'm going to read it out loud. If you were on a star looking back at Earth, you would be seeing dinosaurs. Derpity derp. That's right. According to this cosmology, all the light that's arriving at Earth is old and has millions of years of, well, age. Like, let's get the whiteboard. Let's do a diagram of what's being described. Earth, thing emitting light. We're going to forget about direction now, okay, because that's way too confusing for the globings. Thing emitting light, arriving at Earth, millions of years old. Very good. I'm going to put question mark. Question mark millions of years old. Great. When the Earth had dinosaurs, was it emitting light? Yes, you know how Mars, well, there was light bouncing from it. You can consider that to be equivalent to emitting light, okay? It's through reflection, but still, okay? We can see Mars. So the Earth was, well, sending out light, including dinosaurs. Okay? So, if the light that's arriving at Earth is millions of years old, where's the light from the Earth from millions of years ago? And why don't we aim telescopes in that direction and watch the dinosaurs? And the derpity derps will be going, no, because the light, this is the Earth, with dinosaurs, raw. Okay, see, raw, dinosaurs, raw. This is the Earth now. The light from the raw Earth going away in space. The Earth now. The light from the Earth now is going away. No. We're talking about light arriving at the Earth, like from millions of years ago, including from the direction where the Earth was in the past. Let's look. Let's aim a telescope in that direction to see the light from the Earth when it had dinosaurs. Thanks for that, Del. I enjoyed that. You complete imbeciles. Imbeciles, that's what you are. You globe-believing nincompoops. Just, hello? Does light travel and take millions of years to get to places? Yes. It's not. It doesn't just stop travelling, does it? No, it continues to travel, including from millions of years ago. You look back, you're looking at a star, how it was millions of years ago. Great. Let's look at the Earth and how it was millions of years ago. Anyway, I'm going to go back and play the charlatan, just because it's fun and I'm enjoying watching the chat. Wow. But no, Antonio, you don't get it. You don't get it, Antonio. It's not like that. Stop making it look silly.
That, of course, that means after 9 billion years of the expansion of space slowing down, it's now speeding up. When you take into account the effect of dark energy, that radius of the sphere from which the microwaves were emitted has grown from 42 million with an M light years to 46 billion with a B light years.
Oh, pause. There's someone called in the chat and he's a globing. I'm not gonna give you a wrench because I've been giving too many wrenches and people have been naughty with them. But never mind. Wavik Maelstrom. All light is from the past. That's right, including the light from the past of the raw dinosaur Earth. Why don't we find that light and show it.
And this highlights the confusion that arises from expanding space. We see the light from shortly after the Big Bang. It was emitted a short distance away, and now the location from which it was emitted is now about 1,100 times farther than it was. Further, when we see it as it was then, and not as it is now. Indeed, remember that when the light was emitted, the conditions at the location of the sphere were the same as here on Earth. But the conditions here have changed. Instead of a bath of energy, we now have stars and galaxies. That's also true on that sphere. So, if we could somehow see 46 billion light years away, presumably there are also stars and galaxies. But we don't...
Let me pause again. Wavik Maelstrom is not getting it, so let me help him. He writes, Antonio, you have zero chance of getting why you can't travel faster than light to catch up. You'd have to go faster than light. No, silly. Look, if the light from the stars arriving at Earth is millions of years old, that means it was emitted millions of years ago. Millions of years ago, there was the Earth reflecting light off into space. Where's that light? How is that light not arriving at Earth when the light from the star is? The light from the star is just as old as the light from the millions of years ago Earth. Understand? The Earth doesn't have to have travelled faster than light, but just to embarrass you a little bit. Okay? Regarding your, you can't travel faster than, actually, I won't bother. I already showed it in a previous video. Look, I'll tell you this. This man, the one you're hearing speaking when I'm not talking, the crackpot cosmologist, has a video about how to travel faster than light. He also has a video about how you cannot travel faster than light. That's right. Let's see, it might be in here. In the side. Anyway, I won't get sidetracked. He has two videos. One, why it's impossible to travel faster than light. And a different one, how to travel faster than light. That's right, that's your cosmologist, Dim.
see them there because light from objects that are currently that far away hasn't had time to reach us yet. In fact, and this is a mind blower, we'll never see those stars and galaxies. After all, they are moving away from us very fast.
Sorry, wow, this is just brilliant. So I just ask Wavik Maelstrom, where's the light from the Earth that the Earth emitted millions of years ago that would take, well, millions of years to get here, just like the light from the star that was emitted millions of years ago arrives here. Where is that light? Wavik Maelstrom, his answer is, it's gone another direction. Yeah. Like a torch. Yeah, because it was like a torch, like that half-wit Wally. Yeah. Because light from stars and planets in the globe cosmology, it beams like torchlight. Yeah, it's just shining in a different direction. That's the answer from Wavik Maelstrom. It's gone another direction. There should be in there, but never mind. It's gone in another direction. Just, that's brilliant. I mean, I'm actually laughing. I'm not pretending to be laughing. I'm not that good at pretending. Jeez.
Space is still expanding. We saw that the location when the universe was young, but we can't see them now. It gets weirder. Currently, there is a sphere around the Earth with a radius of about 15 billion light years. Objects that are now outside that sphere at this moment will never see as they look now, no matter how long we wait. I'll repeat that so it can sink in. We can currently see objects 46 billion light years away, but we see them as they were in the distant past.
All right, wait.
And any objects that are currently...
I'm going to pick on Wavik a little bit more. Wavik, Maelstrom. Light from, Earth is travelling away at the speed of light. Space suspension mark. To view our past, you'd have to travel faster than light to see it. Space suspension mark. Light from Earth is travelling away at the speed of light. Right, that's light now. That's right. Travelling away at the speed of light. Great. To view our past? No. You mean to view our future? To view our present? From way in the future back to our present, we'd have to travel faster than light. Yes, not possible, absolutely. However, if you can see stars from millions of years ago, then you can see the Earth from millions of years ago. Where was Earth millions of years ago? At a very far distance. Great. Where sits light? Oh, no, that breaks our theory. Dim dim. Oh, too many hits is here, you see? Too many hits. Rise. I also don't have to prove elevation or level the device. Miles did prove elevation, and the device doesn't need to be leveled. Ugh, too many hits. Look, right now you're in a channel where showed conclusively evidential proof, like actual proof, that camera level is critical when trying to show whether or not there's parallax or whether or not there's dip of any type based on the zoom and the angle of the camera. That's this channel. Too many hits. So when you argue with Beyond the Imaginary Curve, rest assured there are at least two people who know that you're retarded. One being me and the other one being Dell. But carry on. You can carry on arguing with him. Of course, hey, it's a free world. But you might want to pay attention to what the gentleman is saying on the video. That's a gentleman pushing your globe theory, which I'm ridiculing by showing you what he says is your globe theory.
In 15 billion light years, we will be able to see as they are now, although we'll have to wait a long, long time for that light to get to us. And because of the expansion, it gets worse. It means that we constantly lose stars that we can see. Indeed, we lose about 20,000 stars per second. So there are stars that emitted photons at this moment that we will eventually see, but the photons that they emitted at this slightly later moment that we'll never see. One day, the expansion of the universe will make it so that almost all of the galaxies we see in our telescopes today, which I remind you now we're seeing as they were in the distant past, will slip from our view. We will one day only be able to see galaxies from our local group, meaning...
Wait a minute. This is where the whiteboard comes out. We're seeing galaxies as they were in the past. Very good. Let's depict that. Whiteboard. And this is regarding motion and where we will be and where galaxies will be. Okay, now join me in this thought experiment, Globelings. Pretend that you can visualize being out at night looking at stars, looking at speckly lights in the sky. Some of those speckly lights, according to your cosmology, are distant galaxies. Doesn't matter. To you, they're stars. All of those stars, they all have different ages. That means, let's now pick a band in the sky and say there's a band in the sky, and you're going to look at just the stars within that band in the sky. all of the objects in that band are of different ages, which means the light has taken different periods of time to get here. Some 5 million years, some 500 billion years. Doesn't matter. Obviously, well, yeah, we could say 500 billion, because if you can just multiply numbers like your cosmology does, well, yeah, from a different universe. All of the light, different ages, different periods of time to get here, all traveling at the same speed. Okay? Right. If you were on a train and there were Indians shooting at you, and the arrows are arriving at you at the same time, that's a light that you can see. At the same time, at your feet. All these crazy Indians shooting arrows at you at the same time. But some of these arrows are coming from Indians 100 meters away, but some of them are coming from Indians 5 miles away. But they're all arriving at the same time. What does this mean? It means there's great big distances between the Indians shooting arrows at you. Okay? Right. And this is with you just moving sideways on a train. But we're talking about space where you're not just moving sideways around Earth's in an orbit to the sun, also traveling up. So now picture those Indians that were 5 miles away as stars. They're not 5 miles away that way, sending its light here. They're down there someplace, sending their light. Now you can visualize their light to be bubbles of waves, millions of years here, and here's Earth. You can see that if you want, or you can see a beam that bends like this till we catch up with it. Okay? But see this star 5 million years away, and right here in our sky there's light from a star 1 million years. Like, oh, that's interesting. It's like they have different rules to the speed and trajectory of their light paths. Just like the Indians with the arrows would have different trajectories to the arrows. The one that's 100 meters has shot it towards you almost like level with the ground. The one 5 miles away shot it up into the air to come and land at your feet. Are you understanding any of this? Or is this too practical an expression for you? This is an expression of your theory. Is it too physically practical? Is the fact that it's physically demonstrable what I'm explaining, and that physical demonstration undoes your theory, does that make your understanding of the practical explanation unbearable to you? It sounds like it.
Milky Way, Andromeda, and a few dozen minor galaxies in the vicinity. So that's the answer to the question. Our visible universe has a radius of about 46 billion light years, even though it's only 13.7 billion years old. But we're not seeing that distant point as it is now, but as it was shortly after the universe began. And the ongoing expansion makes things even worse. The bottom line is that if we're ever going to try and explore other galaxies, we better get cracking. Okay, so that one was something of a mind blower, but that's cosmology for you. If you like what you heard, please like, subscribe, and share. And be sure to click on the little bell icon to make sure you get notified of every video we post. Otherwise, you only get notified about a few. And I'm sure you wouldn't want to miss some new tidbit about physics.
Whatever, you charlatan. Now we're going to look at this for a short time before I have to go out. Wait until it shows us. It's called How Far is the Edge of the Universe? Hey, why don't you go and take a picture of the edge of the universe?
Asking how big the universe is seems like a silly question.
Hey, look at that retarder sticking his tongue out even though he's not a child. Yeah, Einstein on the t-shirt. It's funny.
I mean, like It's big, really big. How big, you might ask? Oh, I don't know. There's probably a your mama joke in there somewhere. But suffice it to say that it's ginormous. But ginormous isn't really a scientific term, although it should be. So, seriously now, how big
I'm just going to play it. I'm not going to bother switching windows.
is the universe?
Answer. We don't know. That's the true answer. The true answer is we don't know. Nobody knows. It's not possible to know. Could be very, 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 very big and finite, though we can't think of what conditions would cause it to end, to be finite, to be restricted. Could be ridiculously big and just end at some point in the distance, or could be just continuously big and not end. The answer is we don't know. It's not knowable. But these charlatans aren't going to tell you that. They're going to say, we figured out how big it is. This is how big it is. Listen.
First thing you need to realize is that many people misunderstand exactly what that question is asking.
So, the first thing you need to realize, regardless of whether or not you don't understand what the question, how big is the universe, means, okay, you might think, well, that's simple. It means, how big is the universe? Or, what's the universe's size? How big is it? There are other people who don't even understand what that question means. And it's critical for you to know this, that there are stupid, retarded people who don't know what it means. You're not going to be one of those stupid, retarded people, are you? No, you're just going to stay quiet, aren't you? Yes. You're going to keep your head down, aren't you? Yes. You're going to listen, aren't you? Yes. Good. That's right. Now, regardless of how easy the question might be to interpret, how big is the universe, there are people who misinterpret it and don't know what it means. That's what he just said.
We first need to distinguish between the entire universe and the universe visible from Earth.
No, we don't. Those are two different questions. How big is the universe? That has an answer. How big is the universe that can be seen from Earth? That has a different answer. See? Very easy.
Those are different things.
Yes.
So how much of the universe can we see from our vantage point here on Earth? Well, light has a finite speed, specifically about 300,000 kilometers per second, or about 186,000 miles per second, which means that when you see an astronomical object, you're seeing it like it was.
Hey, hold on a second. So, Wavi Maelstrom writes, diameter of the observable universe, about 93 billion light years. It's almost like they've taken the 92, 93 million miles to the sun and they've just said billion. We just take that number. Nobody can verify that number, the distance to the sun. Nobody can verify that, right? Yes. Nobody can disprove it, right? Yes. We'll just say. We'll just change it to B. Nobody will be able to verify or disprove. Great. Very good. Here's your check, sir.
Past. For instance, it takes light from the sun 8 minutes to get to the Earth.
Yawn.
You probably knew that. But that has bigger implications. For instance, that means that there is a sphere around the Earth with a radius of the Earth-Sun distance where light takes 8 minutes to travel to us. And that sphere idea is true in general.
That sphere idea is true in general. That's right. That idea is true in general. Here's an idea. tap dancing seahorses are the best creatures to play the kodo drum. That's an idea. As an idea, it's true. It is true that that is an idea. In that idea, it is true that tap dancing seahorses are the best creatures to play the kodo drum. But in fact, tap dancing seahorses do not exist. Spheres around the Earth do not exist. Spheres between the Earth and the Sun, with the Sun on the end of the radius, do not exist. There's the difference between things that exist, that actually have concrete existence, and things that do not have concrete existence, like tap dancing seahorses. You can say it's true, it doesn't alter the fact they do not exist. There's a difference.
There is a sphere around the Earth with a radius of a light year.
Oh, do you know what? I'm bored of this. It's just boring me. I'm gonna go and look in the chat. I still got this freaking cold, dagnabbit. I'm gonna go and look in the chat. Poke fun at some of the silly globelings. You're retarded. You are. You. Listen, I'm not joking. You've been made intellectually retarded by your education system and by your parents. That's right. Your parents should have had the intelligence to say to you, look, a lot of what you're going to be taught is not going to be true. You can either argue with the teachers and not get good grades, or get good grades. Doesn't matter either way, your importance doesn't change. You're still you. You're still going to do the things you're going to do. Now, if your parents are retarded and they didn't tell you this, and you went through education thinking everything they taught you was true, then chances are you're retarded too. You'll have children, and you will also not tell your children that most of the stuff they're going to be taught at school is false. That's right. Go. Now, would you like evidence that what I'm saying is actually true? It's something that happens in existence, not just in the world of thought. In the US, there are books on contemporary history where it explains how outside the Pentagon on 9/11 there was a crater left by the plane that impacted there. That's right. You might want to, on 9/11, you might want to go and look at photos and see whether or not this is true. You'll find it is not true. There was no crater outside the Pentagon left by a plane on 9/11. What is being taught in those books is false. That's right. And you, Wavik, Maelstrom, and Too Many Hits, and the other dim-dims in the chat, arguing that what you were taught is true, with people that have stopped to think about what they were taught, have found actually a lot of what we were taught has to be taken on faith, and a lot of what we were taught turns out to be demonstrably false, including in physics that light is a wave. That's very interesting. Now here comes charlatans saying light is a wave and what you're taught at school is all true. And then you have dim-dims in the chat saying, well, I believe what I was taught. It's like, that's okay, but don't go around showing that you're retarded. That's just stupid. I mean, if you want to be taken seriously, now, if you were to wear checkered pants and a great big nose and and fluffy hair, white painted face, big grin, and like say you put claxons on under your feet so that when you walked, it went Okay. Now, if you dressed like that and you went around, everybody would know that you were a clown. When you come into the chat saying, but no, cosmology is true, you're doing the equivalent of walking around as a clown. Only you're doing it with your fingers. You're going, You just, and you don't see it. Because it's your parents' fault, not your teachers. Because teachers had parents too. They have to blame their parents. You have to blame your parents. The parents said, no, this is how you fasten the claxons under your shoes. Now go. That's right. Okay, that's it. I'm bailing, folks. It's been fun. Don't know what happened yesterday, by the way. Hangout, more than 1,000 views whilst it was live. Okay. Interesting, but I said at the start of this Hangout, maybe there are flat earthers who work for YouTube. Maybe, huh? Okay, there you go. Thanks, folks. Now I'm going to go and relax. Thank you very much for your time. Adeu.